Welcome to the CWI Deep Dive Podcast series. This is one episode in a series of 11, each covering a chapter of welding inspection technology. These podcasts are designed for inspectors preparing to take the American Welding Society Certified Welding Inspector exam. They are not meant to replace enrolling in a Certified Welding Inspector preparation course or dedicated self-study, but to complement them. Along with our CWI Test Prep app, available on the Apple App Store, these podcasts will help strengthen your preparation. You can continue learning at work, during your commute, or wherever you find time. Today's episode is brought to you by AMS Level 3, providing consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. Learn more at the link in the video description. Disclaimer: this podcast is an independent educational discussion based on concepts from the American Welding Society's Welding Inspection Technology book. We are not affiliated with the American Welding Society, and this podcast is not a replacement for purchasing or studying the original text. Our goal is to provide commentary, explanations, and reinforcement to help inspectors prepare for the Certified Welding Inspector exam. Okay, so today we're diving into Chapter 9. It's titled Welding Metallurgy for the Welding Inspector. And really, our mission here is to get under the hood, understand those invisible changes happening inside the metal. You know, the atomic stuff that decides if a weld is strong and tough or, well, if it's going to fail. For anyone studying for the CWI, this isn't just abstract theory, right? It's fundamental to controlling the process.
Just a quick interruption to introduce a resource to help you take your training further. The AMS Level 3 CWI Part A Test Prep app is now available on the Apple App Store. Designed for welders and inspectors preparing for the Certified Welding Inspector exam, it offers two modes. Study mode gives instant feedback with detailed explanations, and test mode simulates real exam questions with topic-based results to track your progress. All questions align with the AWS Welding Inspection Technology reference, ensuring accuracy and relevance. Download the CWI Part A Test Prep app today on the Apple App Store, and take your study time to the next level.
That's exactly it. You hit the nail on the head. As an inspector, you're not picking the alloys, you're not designing the joint necessarily, but you absolutely have to understand why procedures demand certain things. Why do we need preheat sometimes? Why control interpass temperature? Why track heat input? It all comes back to managing the metallurgy, controlling those internal changes to make sure we get the strength, the hardness, the ductility we need in the final piece. And yeah, today we'll mostly be talking about ferrous metallurgy, iron-based stuff. All right, let's start super small then. Atoms. Every bit of metal is made of atoms held in this delicate balance, right? There are forces pulling them together, attractive forces and forces pushing them apart, repulsive forces apply heat, apply load, and that balance shifts. And that balance is everything for mechanical properties. Think about compression. You push the atoms closer. Those repulsive forces really kick in, pushing back hard. That's why metals are so strong in compression. Now, pull them apart tensile strength. That engages the attractive forces. But if you pull hard enough, past the yield point, you permanently stretch that spacing. That's plastic behavior. The metal has deformed.
And heat adds energy to this whole system. The atoms start vibrating more, they jostle around, push each other further apart. We see that on a macro level as thermal expansion. But this expansion isn't just a curiosity, is it? It sounds like the start of problems for welders.
Oh, it absolutely is. It's the root cause of residual stress. Every material has a number, the coefficient of thermal expansion, that tells you how much it expands when heated. Now, welding is extreme uneven heating. One spot gets incredibly hot, the metal next to it is cold, so you get massive differential expansion, and then when it cools, differential contraction. That locks in stresses, causes warping. And yeah, add enough heat, the atoms vibrate so much they break free of their structure that's melting, solid to liquid.
Okay, so from single atoms, let's zoom out a bit. Solid metals aren't just a jumble, they form crystalline structures. These repeating patterns called unit cells. And here's something that's maybe counterintuitive. Some metals, like iron, can actually rearrange their internal crystal structure just due to temperature changes, even while they're still solid. That's called allotropic phase transformation.
And knowing those structures is key. There are three main ones you'll encounter. First, BCC, that's body-centered cubic. Imagine a cube, atom at each corner, plus one right smack in the middle. That's iron at room temperature, typical carbon steels. Second, FCC, face-centered cubic. Again, atoms at the corners, but now also one in the center of each of the six faces. Think aluminum, copper, those austenitic stainless steels we weld.
Got it. And the third one, you see it less in, say, structural steel welding.
Right, that's HCCP, hexagonal close packed. It's a hexagonal prism shape. You find that in metals like titanium or zinc. Now, when liquid metal cools and starts to solidify, it doesn't happen all at once. Little crystals, called dendrites, start to form. They grow outwards, like branches, until they run into other growing crystals, and that forms what we call grains.
And where these grains meet, you get grain boundaries. They're like interruptions in the perfect crystal pattern. It seems weird that an interruption or a boundary could be a good thing, but grain size really matters for how the metal behaves, doesn't it?
Oh, hugely. It's a critical factor. Generally, smaller grains are better, especially at room temperature or lower temps. Those boundaries act like tiny roadblocks. They make it harder for dislocations or imperfections to move through the metal under stress. So small grains usually mean better tensile strength, better ductility, better notch toughness, even better fatigue life. But flip side, if you need a material for really high temperature service, sometimes coarser grains are actually preferred because those boundaries can become weak points at high temps.
Okay, interesting trade-off. Now, as inspectors, we're almost always dealing with alloys, not pure metals. We add other elements, carbon to iron to make steel, zinc to copper for brass. We're deliberately messing with that pure structure to get better properties. How do these foreign atoms actually fit into the main metal's crystal lattice?
Good question. It really depends on the size of the atom you're adding. If the added atom is much smaller, think carbon, hydrogen, nitrogen, it does what we call interstitial alloying. It literally wedges itself into the small gaps or spaces between the main lattice atoms, like putting pebbles between basketballs. But if the alloying atom is roughly the same size as the base metal atoms, then it's substitutional alloying. The new atom just kicks out one of the original atoms and takes its place in the lattice structure, like swapping one basketball for a slightly different colored one.
So whether it wedges in between or swaps places, the end result is the same. You're creating little disruptions, strains, irregularities in that nice, perfect atomic grid.
Exactly. And that disruption, that internal strain, is usually why alloys are stronger or harder than the pure base metal. It makes it harder for those atomic layers to slide past each other.
Okay, we've got our alloyed metal. Now we need the map to understand what happens when we heat and cool it. Which brings us, I guess, to the iron-carbon phase diagram. And let's be honest, the first time you see it, it looks pretty intimidating. Lots of lines and zones.
It does look complex, but think of it like a weather map for steel. It shows you what phases, what structures are stable at different temperatures, that's the up and down axis, and different carbon percentages, that's the left to right axis. Critically, this standard diagram assumes very slow cooling near equilibrium. We define steels based on carbon content using terms from this diagram. Hypotectoid steel has less than 0.8% carbon. Hypereutectoid has more than 0.8%, and eutectoid steel has exactly 0.8% carbon.
So if we take a common structural steel, maybe like 0.2% carbon, and heat it up from room temperature, what happens according to the map? It starts as ferrite and perlite, right?
Right, room temperature stuff. As you heat it, you hit a critical temperature, 1333 degrees Fahrenheit. That's the A1 line on the diagram. Above that temperature, those room temp structures start transforming into a different phase called austenite, also known as gamma iron, which has that FCC structure we mentioned. Keep heating, cross another line called A3 for that 0.2% carbon steel, maybe around 1600 degrees Erfurter, and the entire structure becomes austenite. The original grains are gone, replaced by austenite grains, which will then start to grow if you hold it at temperature.
Okay, heating seems straightforward enough. Transformation to austenite, but you said the diagram assumes slow cooling. Welding is anything but slow cooling.
Precisely, and that's the absolute core of welding metallurgy for the inspector. The cooling rate is everything. If you cool that hot austenite slowly, like letting it cool in the furnace, the atoms have plenty of time to move around to diffuse. Carbon moves out of the iron lattice, and you form a relatively soft, ductile structure called perlite, often mixed with ferrite. That's generally good from a toughness perspective.
But if you cool it fast, like quenching it in water, or just the rapid cooling that happens naturally next to a weld?
That's where the trouble starts. If the cooling is too fast, the atoms, especially those little carbon atoms, don't have time to diffuse out and rearrange nicely. The iron tries to transform back to its BCC structure, but the carbon gets trapped inside, distorting the lattice into a different shape called body-centered tetragonal, or BCT. This highly strained, carbon supersaturated structure is called martensite.
And martensite is the big problem, right? Because it's incredibly hard, very high strength, but also very brittle. Low ductility. It snaps instead of bending.
Exactly. It's the structure we actively try to avoid forming in the heat-affected zone, or HAZ, of most structural welds because of that brittleness. It's a major cause of cracking. Now, if the cooling rate is somewhere in between faster than slow cooling, but not a harsh quench, You can get other structures like fine pearlite or bainite, which are generally stronger than coarse pearlite but still tougher than martensite.
So, if you accidentally form martensite, or maybe you deliberately quench a part to make it super hard, like for a tool, you've got this brittle structure. How do you fix it? Well, that's tempering, right?
Correct. Tempering is the crucial follow-up step after quenching. You take the hardened part, the martensitic part, and you reheat it, but this is critical. You keep it below that A1 transformation temperature, 33 degrees. This gentle reheating gives those trapped carbon atoms just enough energy to move a little bit, to precipitate out as tiny carbide particles within the structure. It relieves some of the internal strain. You're transforming that brittle as quenched martensite into tempered martensite. You sacrifice some hardness, but you gain back significant ductility and toughness while still keeping a lot of the strength. It's a balancing act.
We'd also like to recognize Skaggs Media LLC as the creative force behind today's podcast. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com.
Okay, let's bring this back to the actual weld. We've talked about uneven heating. The area right next to the molten weld pool, the heat-affected zone, or HAZ, gets really hot, almost melting, but doesn't actually melt. And because it's right next to all that cold base metal, it cools down incredibly fast. Faster than the weld metal itself sometimes.
Exactly. The surrounding cold metal acts like a massive heat sink, just sucking the heat away. So the HAZ experiences the highest temperatures below melting and often the fastest cooling rates. That makes the HAZ prime territory for forming that hard, brittle martensite we just discussed, especially in thicker materials or materials with higher alloy content.
So, as an inspector, a big part of the job is making sure the welding procedure is controlling that cooling rate to prevent problems in the HAZ. What are the main knobs we can turn?
There are essentially 4 key factors the welding procedure controls to manage the cooling rate. 1 is the heat input from the welding process itself. 2 is preheat, warming the part before welding. 3 is the material's inherent hardenability, which we estimate using the carbon equivalent. And 4 is just the physical reality of the metal thickness. Thicker metal cools faster.
Let's talk about heat input. That's something the inspector might actually calculate or verify on the job, right? There's a formula for it.
Yes, absolutely. Heat input, usually measured in joules per inch or kilojoules per inch, is calculated from the welding parameters. The formula is heat input equals welding current, amps, times welding voltage, volts, times 60, divided by the welding travel speed in inches per minute. That times 60 is just to convert minutes in the travel speed to seconds, so the units work out correctly to joules.
Okay. Amps times volts times 60 divided by inches per minute. And what's the relationship there? More heat input means?
More heat input means a slower cooling rate. You're pumping more energy into the part per inch of weld, so it takes longer to cool down. That's generally desirable if you're trying to avoid martensite. So think about it from an inspector's perspective. If you see a welder moving way too fast, their travel speed is really high. What does that do to the heat input?
High travel speed means the denominator in that fraction is big, so the overall heat input goes down.
Right. Lower heat input means faster cooling, and faster cooling increases the risk of
Martensite and potential cracking.
Exactly.
Oh.
So monitoring those parameters, amps, volts, travel speed, is directly linked to controlling the final microstructure and properties. But heat input is only part of the story. We also have to consider the material itself. That's where carbon equivalent, or CE, comes in.
Right, CE isn't something we measure directly. It's calculated based on the chemical composition of the steel. It's a way to estimate how easily the steel will harden, how susceptible it is to forming martensite.
Correct. It's an empirical formula, meaning it's based on experimental results that combines the effect of carbon, which is the most powerful hardening element, with the effects of other common alloying elements. You'll see formulas where you add the percentage of carbon plus manganese divided by 6, plus maybe nickel plus copper divided by 15, plus chromium plus moly plus vanadium divided by 5. The exact factors vary slightly between different formulas, but the principle is the same. Carbon gets full weight. Other elements get fractional weight based on how strongly they contribute to hardenability compared to carbon.
And the higher the CE value, the more likely you are to form martensite for a given cooling rate.
Precisely. And that CE value is often used directly in codes and standards, like in Table 9.1 mentioned in the chapter, to recommend or require preheat temperatures. For example, if your CE gets up above, say, 0.60%, you might be looking at needing significant preheat, maybe 400 to 700 degrees Fahrenheit, to slow that cooling down enough to avoid HAZ cracking.
We talked earlier about uneven heating causing expansion and contraction issues. This creates internal stresses, right? Residual stress is locked into the part even after it's cooled down.
Yes, huge internal stresses. Imagine one part of the weld shrinking as it solidifies, while the metal next to it is still hot and expanded, or already cold and rigid. It creates this internal tug-of-war that can easily warp the part, or worse, lead to cracking later on. Think of figure 9.18 in the chapter, that analogy of trying to fit different length bars together. That's what's happening on an atomic scale.
So how do we relieve those locked-in stresses?
The most common way is thermal stress relief, which is a type of post-weld heat treatment, or PWHAT. You heat the entire welded component uniformly in a furnace to a temperature high enough to soften the metal slightly. But again, staying below that critical A1 transformation temperature, hold it there for a specific time based on thickness, and then cool it down very slowly and uniformly. This allows the metal to creep or relax on a micro level, reducing those internal stresses. Another method used more locally during welding is peening.
Peening, right, that's using a hammer, often a pneumatic one, to basically hammer on the weld beads while they're still warm but solid.
Exactly. You're mechanically working the weld metal. As the weld bead cools and tries to shrink, which puts it under tension, the peening action spreads the metal laterally. This introduces compressive stresses into the surface layers of the weld bead, which helps to counteract the tensile shrinkage stresses. Figure 9.1 again shows this. But critical warnings for inspectors here: you never peen the root pass, the very first layer, because it's too thin and prone to cracking under the impact. And you never peen the final cover pass, because the surface deformation can hide or mask discontinuities, making visual inspection and NDT much harder or impossible. Peening is for the intermediate fill passes only.
Okay, let's shift gears slightly to diffusion again. Atoms moving around in the solid state. We mentioned alloying, but there's one specific element whose diffusion causes major headaches in welding: hydrogen.
Ah yes, hydrogen, our smallest atom, element number 1. Because it's so tiny, it diffuses incredibly easily through the steel lattice, especially when it's hot. Where does it come from? Usually moisture, water, H2O, in the flux coating of electrodes, on the surface of the plate, even just humidity in the air. Also oils, grease, paints, organic contaminants. The heat of the arc breaks down these compounds, releasing atomic hydrogen, H, which dissolves readily into the molten weld pool and the hot HAZ.
And the problem isn't just the hydrogen being there, it's what happens when it cools down, right?
Exactly. As the metal cools, the solubility of hydrogen drops dramatically. The hydrogen atoms try to diffuse out, but if the cooling is fast, they get trapped. Worse, they tend to migrate to areas of high stress or discontinuities like grain boundaries or tiny inclusions. And there, individual hydrogen atoms, H, can recombine to form hydrogen molecules, H2. Now, H2 is much bigger than H. It can't diffuse easily anymore. It's trapped. And the pressure built up by these trapped H2 molecules can be enormous, leading to very high internal stresses.
Which causes hydrogen cracking, also called underbead cracking or delayed cracking.
Precisely. Underbead, because it often initiates in the HAZ right under the weld bead. Delayed, because it might not happen immediately. It can take hours or even days for the hydrogen to diffuse, concentrate, and build up enough pressure to cause a crack, especially if the material also has a brittle microstructure like martensite. So the inspector's playbook for preventing hydrogen cracking has 3 main parts. First, meticulous cleaning. Remove all moisture, rust, oil, paint from the weld area. Second, use low hydrogen consumables. These are electrodes, like an E7Z018, with flux coating specially designed to have very low moisture content, often requiring specific storage like heated ovens. And third, use preheat. Heating the part beforehand, typically in the 200 degrees to 450 degrees after range, does 2 things. It slows the cooling rate after welding, and it increases the diffusion rate of hydrogen, giving it more time and energy to escape before it gets trapped.
Makes sense. Keep it clean, keep the hydrogen source low, and give any hydrogen that does get in a chance to escape.
Before we leave iron and steel completely, you mentioned diffusion is also used deliberately sometimes, like for surface hardening.
Yeah, it's the same principle of atoms moving through the solid lattice, but used intentionally. Tack carburizing is a classic example. You pack a low-carbon steel part in a high-carbon material, heat it up below the melting point for a long time, and carbon atoms diffuse from the packing material into the surface layers of the steel, making the surface much harder for wear resistance. Nitriding is similar, but uses nitrogen, often from ammonia gas, diffusing into the surface. It leverages solid solubility, the fact that one solid can dissolve into another up to a certain limit that usually depends on temperature.
Okay, quick tour of some non-ferrous metals relevant to welding inspectors. Stainless at steel's first. Key identifier is chromium, right? At least 12%. Correct. That chromium forms a passive oxide layer that gives stainless its corrosion resistance. For welding, we often deal with the austenitic grades, the 300 series, like 304 or 316. They're generally very weldable, but have a couple of specific metallurgical quirks. First is the need for a small amount of delta ferrite in the weld metal as it solidifies. Austenite itself is prone to hot cracking or solidification cracking right as it freezes. Having a little bit of ferrite mixed in, usually targeted between 4% and 10%, measured as a ferrite number or FN, changes the solidification mechanism and prevents this cracking. Since austenite FCC is non-magnetic and ferrite BCC is magnetic, inspectors often use a calibrated magnet, a magnetic gauge, right on the weld to verify the ferrite number is within the required range.
Okay, so ferrite number check for hot cracking prevention. What's the other big issue with welding stainless? Something called sensitization.
Yes, sensitization, which leads to intergranular corrosion attack, or IGA. This is a major concern for corrosion resistance after welding. It happens if the austenitic stainless steel is heated or held in a specific temperature range, roughly 800 degrees air to 1600 degrees Fahrenheit. This happens, for example, the HAZ during multi-pass welding. In that temperature range, carbon in the steel has a strong affinity for chromium. They combine to form chromium carbides, and these carbides preferentially precipitate right along the grain boundaries. The problem is, this pulls chromium out of the metal immediately adjacent to the grain boundary, leaving that narrow zone depleted of the chromium needed for corrosion protection, so the grain boundaries become susceptible to corrosive attack.
That sounds bad, especially for something meant to resist corrosion. How do you avoid sensitizing the stainless steel?
There are three main strategies. One is a post-weld heat treatment called solution annealing. You heat the whole part up to a very high temperature, dissolve any carbides that form back into solution, and then cool it very rapidly, quenching it so they don't have time to reform. It's often impractical, though. Second strategy is to use stabilized grades of stainless steel. These have small amounts of titanium, like in type 321, or niobium, sometimes called columbium, like in type 347 added. These elements have an even stronger affinity for carbon than chromium does, so they form titanium or niobium carbides instead, leaving the chromium free in solution to do its job of corrosion protection. The third and very common strategy is to use low carbon grades, designated with an L after the number, like 304L or 316L. These have carbon content restricted to very low levels, typically below 0.03%. With so little carbon available, significant carbide formation just can't happen, even if held in the sensitization range.
So if you're inspecting a procedure for welding stainless steel, especially for corrosive service, you'd be looking for maybe an L grade specified for the base metal and filler metal, or maybe one of the stabilized grades like 321 or 347.
Absolutely. Seeing that L, or the stabilizing element designation, is key evidence that sensitization has been addressed in the material selection.
Or last couple, aluminum and copper. Quick metallurgical points for inspectors.
For aluminum, the big thing is that tenacious aluminum oxide film that forms instantly on the surface. It has a much higher melting point than the aluminum itself. You have to break through or remove that oxide for fusion to occur. That's why AC, alternating current, is often preferred for GTAW or GMAW of aluminum. The electrode positive portion of the AC cycle provides a cleaning action that helps disrupt the oxide. Also needs good inert shielding gas like argon or helium. For copper, the challenge is its incredibly high thermal conductivity. It just wicks heat away from the weld zone super fast. This means you need very high heat input, maybe preheat, just to get it to melt and fuse properly. Also remember that copper alloys are often hardened by cold working, not heat treatment. Welding, being the heating process, will anneal or soften the HAZ, removing that cold work strength. That needs to be considered in the design.
Wow, okay, so wrapping this all up, it seems like the core message from Chapter 9, all this metallurgy, comes down to heat. How much heat you put in and how fast you take it out, that really dictates the final properties.
That's the essence of it. Understanding those crystal structures, the phase transformations, especially that austenite to martensite transformation, and how the welding variables like heat input, preheat, and material composition CE influence the cooling rate, that's fundamental knowledge for a CWI. It's why the procedures are written the way they are.
So, to leave our listeners with something to chew on.
Yeah, think about this. We've seen the huge difference in properties between slow cooling giving soft, ductile perlite and rapid cooling giving hard, brittle martensite. Considering that difference, what seemingly minor welding variable may be something easily overlooked on a busy job site, do you think poses the greatest risk of causing a catastrophic failure if it's not properly controlled? Something for you to ponder as you continue your studies.
Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training, and mentorship, or compliance solutions like NADCAP and Federal Aviation Administration readiness.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support. NDT Level 1, $1 per month, NDT Level 2, $2 per month, and NDT Level 3, $3 per month, or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.